In today's talk, we will be covering an introduction to the GC chromatographic process. We will also cover the various GC injectors and their functions. GC detectors will be covered in part 2 of this series on May 14th. We will also be presenting separate sessions for GCMS and GC column selection in our fall semester, so stay tuned. What is the chromatographic process? A mixture containing different components which require separation, identification, and quantitation. Conventional or non-mass spectrometry detectors do not do an adequate job of identifying components because many components can elute at the same time on a column. And with a conventional detector and a single-phase column, there is no additional identifying parameter besides retention time. You can do a better job of confirming if a particular component is present by using a confirmation column. A confirmation column needs to have a different column phase. This difference will allow for the sample component peaks to have different retention times on each column. Quantifiable responses should be similar on both columns. Forensic chromatographers use this technique in identifying ethanol in blood. It is important that the components focus at the head of the column before proceeding down the column. Components which do not focus will tend to be broad and may even split. If this occurs, you may want to use a thicker film column to focus the peaks and a low oven temperature. When using a mass spec detector, care needs to be taken with thick film columns, for the thicker stationary phase can make the source become dirty quicker. Also, our oven can achieve a low temperature 3 degrees above ambient. If using a thick film and a low oven temperature still does not focus the peaks properly, a different column may be needed, or liquid cryogen like either CO2 or nitrogen may be needed. Another function that can cause band broadening is the injection process. The injection process needs to be quick. Using a split injection accelerates the velocity through the liner, evacuating the liner thicker and getting the components onto the column quicker so there isn't a lag time in the injection process. A column should be chosen whose stationary phase will somewhat retain the analytes of interest. If some peaks are not Gaussian, yet others are, the phase of your column is incorrect for this component and an alternate phase should be chosen. Therefore, if you are analyzing polar components, a polar column phase should be chosen. If the components in your mix have the same polarities, i.e. a normal hydrocarbon mix, their elution order depends upon boiling point. If two components have the same or similar boiling points yet different polarities, the component which is more similar in polarity to the column phase will be retained longer. The need for conformational chromatography. The effluent may be split onto two columns of different phases. Components which co-elute on the first column will probably separate on the second column and vice versa. There are many different splitters available. A universal Y splitter is used in the above example. A guard column, which is a piece of column with no stationary phase on it, is inserted into the injector port. The Y portion of the splitter is affixed to the other end of this guard column. The analytical columns get installed on the legs of the splitter. In this example, components D and E co-elute on the non-polar column. However, they separate on the polar column. Conversely, components A and B co-elute on the polar column where they are separated on the non-polar column. Some people prefer a two-hole ferrule where both columns get inserted into the same ferrule, then inserted into the injector port. Another use of conformational chromatography is pesticide analysis by EPA method 508, which requires the identification and quantification of pesticides. Some pesticide methods allow for an electron capture detector, while others call for a mass spectrometer. Method 508 is an ECD application, and the analyst must use a conformational column to confirm the identity and the quantity of the eluting peaks. Before considering a target analyte to be detected and reported as a positive hit from the primary column, That compound must also be detected at the appropriate retention time on the confirmation column. If both column retention times do not match, then the peak is classified as not detected. It is much easier to use a mass spec, which is EPA method 525, because this detector uses an ion fragmentation pattern like a fingerprint, and a conformational column is unnecessary. In the blood alcohol application, forensic scientists analyze blood alcohol samples on two separate columns, typically a BAC1 and BAC2. Ethanol elutes at different retention times on each phase. In this example, ethanol elutes at 1.64 minutes on the BAC1 column and 2.15 minutes on the BAC2 column. When a sample is analyzed and a peak elutes at 1.64 minutes and 2.15 minutes, respectively, the scientist is 99% certain that this component is ethanol without the requirement of a fragmentation ion from the MS. This is because it is extremely rare that two components will elute at the same retention time on two separate phases. Just to note, the unidentified peak on both columns is the internal standard N propanol. Utilizing mass spectrometry instead of selective GC detectors is preferred for proper identification due to being able to compare spectra required to the NIST library for positive identification. A mass spec detector is more selective than an ECD. I would say that one advantage of an ECD detector is that it has a bit more sensitivity to electronegative compounds such as pesticides than a mass spec. However, other techniques can be employed to get the same or better detection limits for these analytes using MS, such as large volume injection and negative chemical ionization. A brief summary of the GC sample introduction system is we inject and volatilize our sample mixture, we focus the mixture on our column, separate the analytes, and detect a signal from the detector and send the data signal on to processing and reporting. Here is a quick look at the many varied GC injector systems and techniques available for most GC systems. They are quite diverse and have many specific sample types associated with each. We will only be talking about the liquid injection varieties in this talk. The four main liquid injectors are the packed, split-splitless, temperature programmable split-splitless, also called the PTV injector, and the programmable on-column injectors. Packed injectors are flow controlled, while capillary or split-splitless injectors are pressure controlled and use a calculation to program the pressure so that the chromatography is controlled via flow or linear velocity. However, we have a proprietary process where we can control our injector in real flow. The function of the injector is to volatilize and transfer sample to the analytical column. Techniques we use include hot flash vaporization, controlled vaporization, large volume, and on-column injections. Packed injector pneumatics are flow controlled. When there is a change in column flow, the pressure at the head of the column is increased to maintain a constant flow through the column. As you can see here in this diagram, as the temperature of the GC oven increases, the column flow stays constant while the pressure increases. The packed column injector is a very simple design and its functionality is restrictive. Packed column popularity has been steadily decreasing. The majority of analysts realize the benefits of a capillary inlet in columns and have transferred their technology to accommodate capillary technology. However, old USP methods mandate the use of packed injector ports. If you are required to use one of these older applications, you would have to validate the method to make the switch to a capillary injector. In my opinion, it is worth your time to go through the validation process up front rather than struggle with a dated application. In addition, some gaseous applications rely upon packed column technology. Both packed and 0.53 mm ID columns may be installed in a packed injector. One advantage of packed columns is that they are very forgiving to non-volatile analytes and have a large capacity. Capillary injector pneumatics. How does it work? A programmable module regulates the pressure by calculating for column dimensions and oven temperature. Your column dimensions are known, i.e., you're using a 30 meter by 0.25 millimeter diameter column. The column face thickness is not required for the calculation. This information is inserted into your GC acquisition method. A constant or programmed linear velocity or flow is established by the user and inserted into the appropriate place in your GC method as well. A mathematical equation determines what pressure is needed to achieve a set flow or linear velocity at a specified temperature. The pressure is then increased during the run as the oven program is initiated to maintain the required flow. An advantage to our pneumatics is that we sense the pressure at the head of the column, so if the split flow varies, the flow down the column doesn't, and your retention times will not be shifted. Fortunately, we were able to establish real or actual flow control on our capillary inlets. The challenge using the equation is that column ID and length are not exact. Since the equation relies upon this, the flow will not be what you actually set it to. There is a way to correct for this, but if you have a GC that has real flow control on their capillary inlet, that step will be unnecessary. In addition, if you need to clip your column, you don't need to worry because you'll be in real flow control and the flow controller will automatically adjust the pressures. In summary, PPC modules give flexibility in running your analysis and flow control, mils per minute, linear velocity, centimeters per second, and even pressure, PSI. Changing between helium, hydrogen, and nitrogen carrier gases is easy. Just recalibrate the PPC modules to your choice of gas. Column flows and split flows can be changed throughout your method if needed for separation. However, you need to ensure peak efficiency is not sacrificed while doing this. We will be covering this more in our column selection webinar. Also, if you have a broad boiling point mixture, it is helpful to increase the flow before the higher boiling point components elute, as long as they can separate at that increased flow rate. It is helpful to study Van Deepner's plot when selecting a flow rate or a linear velocity. A septum purge is required on a capillary injector because of the higher efficiencies achieved by capillary columns. They detect smaller quantities of material, and the septum purge helps reduce the amount of contamination from the septa from entering the column. Because of its location, sample is not lost. A split vent is required on a capillary injector for two main reasons. Capillary columns do not have as much phase loading capacity, hence their phase becomes overloaded, yielding overloaded peaks. Phase overloading is evident when you see what is referred to as shark fin shaped peaks and non-Gaussian shaped peaks. Split vents allow the accuracy of a 1 microliter syringe injection to actually be 0.01 or even 0.001 microliters. However, this diminishes the sample volume entering the column since a portion of it goes to the split vent. This is amazingly accurate. Capillary columns are quite sensitive to void volume. Liners contain a lot of dead volume. By increasing the linear velocity through the liner, this dead volume is minimized and the analytes are swept from the injector quicker, and therefore sample focuses on the column in a sharp band and peak shapes are more optimum. Split injections allow us to introduce a 1 microliter volume of sample, but not allow all of the solvent and analytes to load on the column. A large solvent front can swamp a column and take 5 or more minutes to elute from the column. Minimizing the vaporized amount of solvent is critical to achieving proper chromatography. We also may not need all of the analyte concentration to reach the detector to meet our quantitation limits. With a split injection, we can only allow, say, 1 part in 100 to make it on the column, while the other 99 parts are swept away. This allows for sharp peaks, minimized background, and excellent integration of peaks. A split ratio is determined by the amount of analytes in your sample and the required detection limits you need to achieve. Split injection offers the best precision, saves columns and your analytical system from possibly becoming overly contaminated, and can decrease the amount of air getting to your mass spectrometry system. Splitless injections are not as precise as a split injection or solvent purge injections due to all materials in the syringe being transferred to the column. Peak broadening and increased background can cause integration variances, which can lead to varying integration counts. This technique is needed when working with ultra-low concentrations in the part per trillion detection range. The GC method program sets up the parameters described here. When a GC run is completed, the GC defaults back to its initial conditions. By using a negative timed event, the split vent can be purging during cooldown to keep the injector and system cleaner. At 0.5 minutes before injection, the split vent can be closed and then reopened after the injection process. It is preferable to optimize the splitless time before the split vent opens up again. Start with a splitless time of 1.5 minutes. Make injections reducing the time in 0.1 minute intervals. When your first target starts decreasing in area, you just went too low in time. Let's talk about temperature programmable splitless injections, or PSS injectors. They are also known as the PTV, which stands for Program Temperature Vaporization. The PSS injector is a temperature programmable splitless injector. It works the same as the previously discussed splitless injector, but this one is temperature variable at any time during the run. The previously described splitless injector is set at a constant temperature during analysis. With the PSS injector, we can do hot volatilization, temperature programmed, split, splitless, on column, and even large volume injections. It's quite a universal injector. The PSS has a low mass to heat ratio and heats and cools rapidly. It has a cooling fan and cooling fins to help dissipate heat. It can also heat up to 500 degrees C at 200 degrees C per minute. There are some disadvantages to a hot volatilization injection. Some organic compounds break down above certain temperatures. Pesticides are a difficult analysis because some major pesticides of concern, like DDT and Endrin, will break down when they hit the hot injector. DDT breaks down to DDE and DDD, while Endrin breaks down into endrin ketone and endrinaldehyde. Syringe fractionation can occur. Using the fastest speed on your autosampler prevents this. Autosamplers not only provide productivity, they do inject better than human beings and are way more precise. What is backflash and what effect does it have on your analysis? The solvent your sample is in is critical as well. With a hot injector, the solvent can expand into a volume that is larger than the volume of your inlet liner. The expanding gas can escape your liner and contaminate the liner body, but also cause poor chromatography and poor results due to loss of analyte. Carryover from this sample to the next sample is a real possibility. This will also result in poor precision and recovery, especially for the higher boiling compounds, because all of the sample is not getting into the column. And even worse, it can backflash into your pneumatics and tubing if the expansion is large enough. We'll be going over backflash more in depth in a few slides. All solvents have different expansion volumes. A solvent expansion calculator can assist you in determining the proper column flow. Temperature and/or pressure required for you to contain the solvent expansion for the liner size you have in your injector. In this example, the methylene chloride expansion volume at the given set of parameters will exceed the set volume of the 2 mm liner. An ideal goal is to be less than 80% of the liner volume. The parameters to consider are injector temperature, injection volume, column head pressure, and solvent. One way to overcome backflash is using a pressure pulsed injection to reduce the expansion volume of the methylene chloride. We kept our injection volume at 1 microliter and the inlet temperature at 250 degrees. By increasing our inlet pressure from 10 psi to 40 psi, we have now controlled the solvent expansion to below the 2 millimeter liner volume. About 1 minute or so into the analytical run, we can reduce the inlet pressure back to 10 psi for the rest of the analytical run. As you can see by the ideal gas law, that if the pressure is increased, the vapor volume is decreased. Most of us use constant flow mode. On a 30 meter by 0.25 millimeter ID column, using a pressure pulse flow of 5 mils per minute will provide enough inlet pressure to reduce expansion volume. After 1 minute into the run, this can be reduced to your analytical operating flow for your chromatography. Let's talk some more about the benefits of a controlled volatilization, another means to eliminate backflash plus more. If we inject a sample into a cool injector, we eliminate the effects we described earlier of flash vaporization escaping the injector liner and also thermal breakdown. We can also use this technique for a large volume injection. Once the sample is injected and the syringe is removed, we can increase the temperature of the injector to allow us to control the volatilization of the sample. Recoveries are enhanced, backflash is eliminated, and syringe fractionation and thermal breakdown are prevented. I have one last sample introduction technique to discuss today. With the addition of a midpoint carrier device like the PerkinElmer Swafer or Prevent, we can introduce a carrier gas pressure between the injector and the analytical column. With this device, we can maintain carrier flow to the GC column and detector, critical for mass spec for sure, while performing a backflush to the inlet. In this case, we can perform column isolation, do a solvent purge, or even do large volume injections. With the injector cool, we inject our sample into the injector. The split vent is opened up, and our solvent is mildly vaporized and flows out the split vent, maintaining the semi-volatile components in the injection liner. After a select time to complete the volatilization and removal of the solvent through the wide open split vent, we drop the midpoint pressure, close the split vent, increase the inlet pressure, and raise the inlet temperature to 320 degrees, or the required temperature to volatilize your targets. We now allow the analytes of interest to pass through the deactivated fused silica and Swafer and reach our analytical column before making its way to the detector. Once the highest boiling analyte of interest has made its way to the GC column, we have the ability to raise the midpoint pressure, drop the inlet pressure again, open back up the split vent, and even heat up the injector higher. In this mode, we are baking out the injector and liner to remove high boiling inert materials from the injection that are not analytes of interest, but will serve nothing but to contaminate our column and foul up our detector. In this way, we can keep a much cleaner GC system and eliminate active site materials in the injector and our column. With the midpoint Swafer device, we can perform injector maintenance by replacing the injector liner and septum if needed without having to cool down the detector. This is especially critical with a mass spectrometer, which can be oxidized by the introduction of air and moisture while pumped down and hot. Having to shut off a mass spec for injector maintenance can cost operation time. In this slide, we see no uptick in oxygen or nitrogen when the septum cap and liner is removed. This is also beneficial with ECD detectors since they respond to oxygen. With column isolation mode, there is no need to reduce the temperature of your ECD and the background will remain stable. No downtime. In summary of the PSS injector, it is ideal for rapid heating and cooling whenever tough matrices are encountered. If you have thermal expansion, thermal degradation, or heavy hydrocarbon non-target analytes, this is the best injector solution for you. One last note on the PSS injector. Solvent purging utilizing a midpoint pressure device is a much better injection option to increase your method detection limits than a splitless injection. Breakdown issues, vapor expansion, sample loss, chlorinated solvents, and ECD issues, and column isolation and backflash are all problems that plague a straight splitless injection.